it's a complicated problem. And in this particular case, the proposal I've just written, we're collaborating with an Israeli scientist who has a very sophisticated lab setup that just cranks through biopharmaceuticals and all that stuff, and it's specifically set up for those target compounds. So he has it down to a very low cost process. So we would literally be taking samples and shipping them to Israel to get them analyzed. And then we can do them for a few dollars a sample, because his lab is specifically dedicated, has technicians and machines all set up. And the costs are being amortized by government grants from Israel. In Israel, they've been doing land application of treated wastewater for forever, almost from the start of the country, in that they're so water stressed, right? And so they've never been like we are. We're kind of like, get rid of the water. They see all water as a resource. But they're seeing some very curious impacts on plant development from the long-term use of some of these wastewaters. And so they're trying to sort out, is it bioaccumulation, is it clogging of the pore space, is it salinization, just the salt content? What is it that might cause long-term negative impacts from using wastewater as a source of irrigation water? And so, and then furthermore, is there a possibility that they are impacting the groundwater system? So, like in our little wetland in Woodburn, was it possible that we were transporting pharmaceuticals to the river? Well, as it turns out, I mean, the water is going to go to the river probably anyway. But if we know more about it, perhaps the wetland treatment is more effective than, well, certainly more effective than simply putting it straight in. But how effective? And what plants might really be able to make that even more effective than otherwise? When we talk about a wetland, the specific plant species are really a big deal. And they're completely different. And they have different rooting structures, oxygenation structure. So they create totally different biological habitat, which gives rise to completely different treatment effectiveness for nutrients and everything else. One of the things that people don't think about much with these wetlands is that if you're in a normal cropping area, you harvest, right? And you export nutrients. But if you're in a wetland and you're continually adding nutrients and there's material there for growing and dropping into the water, eventually, mass is conserved, and so, all that nitrogen or all the other nutrients are going to have to be accounted for. Now, some of them will, through transformation, go into a gas phase, and you'll end up with, nitrogen gas coming off. But it is possible also that early treatment effectiveness of wetlands can diminish in time, particularly with respect to nutrients, if the system is not kind of specifically designed to account for the fact that it may be building up organic matter.
These agricultural sites, there's typically a hard clay pan layer associated with tilling, and so those projects have a different vertical conductivity than, say, the least disturbed wetlands, which you see the water moving deeper into the soil profile throughout this season. And it has implications for nitrates, for example, the runoff of nitrates, whether they infiltrate and move deep into the groundwater or accumulate at some surface, just at some horizon just below the surface. Those agricultural wetlands function very differently, and that even the restored wetlands are quite a bit different from these least disturbed sites, so that the restoration doesn't appear to have recreated things like wormholes and other components of the soil structure that are really important for creating these small storage spaces, but also these conduits for moving water through the system. There are some differences at those restoration sites, and over time we expect that they'd mature and they would begin to look more like the least disturbed sites. Some of the projects that we're working on here are these least altered sites which have never been in agriculture, but those are really hard to find. So for the most part, the restored sites we've been working on were reclaimed by agriculture and have now been converted back to more natural wetlands.
Boreal peatlands cover a vast area of the world's northern hemisphere, both in the US and actually in Asia. Siberia has huge expanses of peatlands. With global change, we're expecting to see those areas get warmer, and we're actually expecting to see precipitation increase. And as those areas get warmer, you might expect to see greater decomposition. And if they're wetter too, and if the areas have a larger expanse of the peatland surface is anaerobic, then the product of decomposition can be methane rather than carbon dioxide. Methane is a more powerful greenhouse gas than carbon dioxide. So there's the potential for northern peatlands to switch from being a sink for carbon, right, which they're a sink for carbon right now. There's the potential for northern peatlands to turn into a source of carbon to the atmosphere and to produce methane, which is a stronger greenhouse gas than CO2. And that would be that would have a significant impact on climate change. That would be something that would be of interest, I think, to people in not only in the U.S. but in Canada, because Canada has much more extensive areas of peatlands, and people in Eastern Europe and in Russia. Boreal peatlands are kind of unique in the sense that they are accumulations of a lot of organic matter through the buildup of sphagnum moss and the other vegetation that occurs on those bogs, and that eventually they dome up and they're isolated from groundwater or other types of soil nutrient input, and they eventually become only rain fed, and that restricts what can grow on those sites. So the vegetation's unique, the water chemistry and soil chemistry is unique, and then their carbon storage properties are unique. They form, the research project that we did in the eastern U.S. and Canada was extensive. It was probably the definitive work of its time in 1980, 81, 82, and in terms of describing the vegetation, the ecology, and the biogeochemistry of sphagnum bogs. There wasn't a lot left to look at that point. Now I think one could go back and one could repeat those kinds of studies and look at particularly impacts of climate change. And those studies were over 20 years ago. And it would be very interesting to see what the current rates of decomposition are. One of the things I actually did on that project was a study on peat decomposition and cellulose decomposition in these peatlands. It would be very interesting to see what rates of decomposition are now. It would be interesting to see whether some of the sites from which we collected long and short cores have actually lost some of the surface peat through decomposition, because that's what one would expect with warmer temperatures and particularly in the mid-continental area. I would think that might be something we would expect to see. So there are subtle differences, just slight differences in precipitation could increase the growth of sedges over the moss, and as long as if they raise the water table in these peatlands to a higher level. And so you could change the species composition from dominated by sphagnum moss to something dominated by sedges and shrubs, depending on what the climate shift looked like and what the water table looked like in those peatlands. So it's a dynamic and perhaps somewhat unpredictable relationships between the site conditions and which species will outcompete one another under the different conditions. So we don't really know.